Okay, we're still evaluating limits analytically. You have your factoring approaches, you're simplifying complex fractions, your conjugates, you're multiplying stuff out. And then in addition to that, we got these two trig identities right here. So the important thing is for these identities to hold true, if the answer is going to be 1 or 0, the limit has to be x approaches 0. If I'm approaching x approaches pi over 2 or 3 pi over 2 or something else other than 0, these identities are not going to be true. All right. It could still be 1 or 0, but most likely it's going to be some other answer there. Okay. If that's not 0, then you just plug in like we did before and you get an answer. The nice thing about these identities, these don't always have to be an X. These two items right here simply have to match. Same thing right here. These two items right here simply have to match. So if they match, then that limit answer would be 1. That limit answer would be equal to 0. You did this in a prior homework assignment. You made an XY chart for this particular function around 0, and you had to calculate in radian mode, and you show that that answer was equal to 1. So you kind of did that, and we'll prove these in a different method later on in the year. But the reason I'm just these few examples here, see how I have a 5x and a 5x? So those two items match. So that limit as x approaches 0, that is equal to 1. It also works if you flip them around. If you do the reciprocal of those two fractions, it works. So for example, if you had something like this, that identity would still be equal to 1. If you forgot the identity, if you got them confused, you could go make an XY chart, choose like 0.0001, negative 0.001, and see if those answers are approaching 1 or 0 right there. And then the same thing, again, if these two are matching, that answer is going to be equal to 0. As you work through these problems, you just have to be careful how you're justifying things, okay? If we're not justifying things properly or the notation is off, I don't want to have to deduct for that, okay? Here's what you're allowed to do. You could take numbers and you could pull numbers out in front of that limit notation. You can't ever pull a variable out in front of that limit notation. If you do that, there's no points right there, okay? So also, this trig angle, you can't ever change that trig angle, all right? So you can't take this 4 right there, that's part of that trig angle, and you can't pull that out in front. It's not like a 3, that's not part of the trig angle right there. So if you ever like pull variables out in front, that's really not good. If you ever take trig angles and change the trig angles, like you pull a 4 out of a trig angle, that's completely illegal algebra there. You're not allowed to do that. So as long as you're just doing the limits of the variables and you're pulling the numbers out and working in the identities, then I think you're going to be safe there. But just be a little bit careful as you're doing these problems. Make sure you justify it properly and show the work properly. But what I'm allowed to do right here is this 3 is not part of a trig angle. I can take that and I can pull that out in front of my limit notation. And notice all these examples as x approaches 0, which means I'm just going to try to work in the identities. If I had x approaches pi over 2 or something, I would just take the pi over 2 and plug it in place for the x's and get the exact answer like we did before. So notice that this is our identity. That's equal to 0. So we have 3 times 0, which is equal to 0, and then that's our final answer. If it doesn't look like the identity and I can't plug in because I'm getting 0 in the denominator, then you have to just play around with it, do legal algebra. So we know that this tangent right here, we can convert that to sine over cosine. And then these cosines will cancel out. And what I'm left with is sine of theta over theta. And I haven't plugged in yet. I haven't used an identity yet. I haven't taken the limit yet. So remember that limit notation is still there. And then this is working in that first identity. Limit at theta approaches 0, sine of theta over theta. Notice that these two things match. So that limit answer is equal to 1, and then we're done. Let's be a little bit careful right here, okay? So it doesn't matter what your answer is, your work has to be justified properly, all right? They always look at that work on the actual AP exam. Now, what you can't do, you can't take that 4, you can't pull that out in front, you can't ever change that trig angle. But we set for this identity to be 1, we need those two things to match. So what you need to do, since you can't change that guy up top, you need for this right here to be a 4 in that denominator so that those two things match. But now you just change the problem, right? But see, that's not part of a trig. Now you just put a 4 in the bottom of a fraction. So if you change the problem, then change it back. You got to compensate for that. also put a 4 on the top. So really I'm just timesing it by 1. That's 4 over 4. But see, now this 4 is not part of a trig angle. It's just a number out in front, just like that 3 was. So I'm allowed to take this 4 and pull that out in front and carry down my limit notation. And I'm gonna leave everything else the same. I have the sine of 4x on the top, and I have that 4x on the bottom. See, it's not a lot of work that you gotta show here, but the couple steps that you do need to show, you gotta make sure you justify that correctly, and then we're gonna be okay. So be careful with that. I'm gonna be a little bit picky about that when we're grading the homework there, so be careful with that. And then this is your identity, which is equal to 1. So then you get 4 times 1, which is equal to 4 right there. All right, so right here, limit of theta approaches 0, so the identities are in play, and I got this 5 on the bottom. You can't just take a 5 and put it inside that angle. You're not allowed to change the trig angle right there. So that sine of theta has to stay the same, which means you don't want this 5 right here. But see, this 5 is just like a 1/5. It's not part of a trig angle. You're allowed to just pull that out in front. The same reason why we just pulled that 3 in front. If that 3 was on the bottom, then I pull out a 1/3. So if you just pull out a 1/5, and then you have the limit as theta approaches 0, and now you have the sine of theta divided by theta. Sometimes you might see something with something in the numerator and the denominator, and you can combine both of those techniques right there. But see, this is your identity, which is 1, and you have 1/5 times 1, which would be 1/5 for your exact answer right there. And I just made up an extra example there because sometimes people get confused with the variables, how to approach that. I can't take like a variable and pull it out in front of the limit notation. So what you can do though, is you could just do the limit of a couple of different things if you need to, okay? So right now, if I plug in 0, I get 0 on the top and I get 0 on the bottom. All right, the thing is undefined there, but remember, just because your function is undefined doesn't mean you can't have an answer for your limit. So here's what we're gonna do. You're just gonna play around with this, do legal algebra, do some pre-cal stuff. I know that tangent squared is sine squared over cosine squared. So I'm gonna do that. I'm gonna go sine squared over cosine squared. And that x is in the denominator, so I'm gonna leave that x in the denominator. I haven't taken a limit yet. So I got the limit as x approaches 0. So I got a problem with that x because if I plugged it in there, I'm getting 0 in the denominator. So I'm trying to work in these identities somehow, but it's not quite here. Now, another thing that we could do here, this sine squared, we can rewrite that as sine of x times sine of x. And all I'm trying to do is just manipulate this somehow to work in one of these two trig identities. That's all that's going on there. So see how I have sine of x over x? That is my trig identity. So that's good. I'm seeing that right in front of my face. That's something good. Now, instead of taking stuff and pulling out from that limit notation and not having that proper notation there, all you gotta do is just leave that limit notation out front. And then you have your sine of x over x. We're just gonna rewrite that. And then what you have left is you still got an additional sine of x over this cosine squared. Now, what you're allowed to do, this is technically all inside that limit notation, okay? So you're gonna do the limit of all of that stuff. But if I have the identity right here, I'm not allowed to take this whole entire chunk and pull it out in front, but what you can do is just do another limit, all right? So as long as you're doing the limit of all those variables, you're gonna be okay. Now this limit notation right here, that's our identity, which is equal to 1. And this right here, I'm just gonna plug in like we did in the prior section. So, because if I plug in 0, cosine of 0, guess what? That's equal to 1. So I'm getting 1 in the denominator, which means I don't have to worry about 0 on the bottom. So I'm okay to plug in here. I don't have any issues. And if I plug in 0 to the top, sine of 0 is 0. So we have 0 divided by 1. So we get 1 times 0, which is 0 for the final answer there. So like I said, you're allowed to pull numbers out in front. That's fine. Don't mess with the trig angles. And then just keep that limit notation there. Show a couple of steps there. Model the notes the best you can there. And if you have stuff with extra variables in there, you're allowed to break it up like that. But just do the limit of that. Do the limit of that. Do the limit of a couple things if you need to. And then just kind of show what you're getting. And before I forget, I'm not sure how much we'll need this in this section, but throughout the year, the Pythagorean identities are going to be pretty valuable for us there, right? They're going to be there quite a bit in most of the chapters there. So I would just kind of have those 3 memorized from your pre-cal days. And then last example we're going to do here, this doesn't have anything to do with the trig identities, but this is something that you touched on last year, this is your main definition of your derivative, which we'll get to in chapter 2. But this chapter 1 just has us practice the limit answers, the limit algebra and stuff. So when we hit chapter 2, we're already going to know what's going on. So if I give you a function and I tell you to find that, okay, so I'm going to do the limit as delta x approaches 0. Now this is a derivative, even though they're not calling it that. It says f of x plus delta x. So remember, if I gave you if I told you to find f of 5, what would you do with that 5? You would take that 5 and you would plug that in place for x. If I gave you f of Superman, what would you do with that Superman? You would plug that Superman in place for x and you would get the square root of Superman. So when I gave you f of x plus delta x, you got to take that x plus delta x and you need to plug that in place for the x there. And then it says minus your f of x. Well, your f of x is simply equal to your square root of x. So that's your original function. And then you got that delta x on the bottom. So this is going back to the prior section where you need to evaluate this limit. And I see radicals, so I'm going to do my conjugate approach, right? So I'm going to multiply the top and the bottom by the same thing. And I'm just going to switch that one symbol in between the two terms. Like that, because remember, that's just equal to 1. And then remember, the bottom part, you're just going to smush that together. So we have our delta x times all that weird stuff. And then the top part there, you have a binomial times a binomial. So you're going to multiply that out. So if I take a radical times a radical, that's going to make that radical disappear. And then we're going to have like a positive that and a negative that. Those middle terms will wipe each other out. And then you have a negative radical x times a positive radical x, which is just going to be a minus x. Now, in the next chapter, I'm going to loosen the reins a little bit. I won't necessarily make you write the limit notation every single time, but chapter 1, we got to make sure we practice that because that's really going to mess us up if we don't remember to take the limit at the end of the problem. So remember what I asked you to do. Write the limit notation each step until you're about to do that step where you plug in. Now right here, you have x minus x. So those are gone. So the only thing you got left standing on the top is the delta x. And so that delta x could cancel out with that delta x. And I haven't plugged in anything yet, haven't taken my limit yet, so I still have my limit notation there. And now we can plug in the 0 for the delta x, not the x, but the delta x. And so that's going to give us square root of x plus the square root of x, which is going to be 1 over 2 radical x right there. So hopefully that example, hopefully all those examples help you out for that homework section.